Okay, now last time we have finished the 14.7. That is the maximum minimum value in partial derivatives. So I hope you can find more exercises or practice, and we can also review, maybe review maybe next week. But for this week, what I would like to do is we are moving to chapter 15. Okay, so now we have chapter 15, and as I mentioned, I think last week, because I have prepared the quiz. So the quiz, chapter 12 and 13. This will be online quiz. Okay, so by online quiz means that this is simply similar to what we have done in uh, chapter 11. So this will be like a homework. So you can do it anywhere. Okay, you can do it anywhere. I will I will put the link probably this weekend. Maybe from Friday to maybe I will put 3 or 5 days, including the weekend. Maybe Friday will be uploaded or attached, so you can see from Friday night, and you can work out the quiz for 3 or 4 days. Okay, so please check out. What you need to do is just click the link, and you can prepare anything you can prepare. Um, you can prepare calculator, even you can prepare notes if you want, because I believe the this is like an exercise, but I will grade as a quiz, but maybe smaller percentage. Okay, so this percentage will be smaller than the physical quiz. It will be smaller because it's online, and I believe you can do anything. You can use calculator, um, look up your notes. Okay, so that's the quiz. Since each questions will have a time limit, you need to be aware of that, the time limit. And some question is multiple choices. Some questions is fill in the blank. So please also be careful of that. Okay. Okay, and after this quiz, I will also prepare another quiz for chapter 14, but this will be maybe mid of May. So this will be middle of May. Middle of May means around um, maybe around 23. So probably have a chance to be physical. But if not, then we will have online quiz. This will be flexible. Okay. And of course, since the adjustment for the um, the situations will be, we have online lectures until 22, right? 22 until 22 online lecture, and hopefully final exam still be physical. This should be in June, right? Okay. So um, regarding the midterm result, you can email me if you want to know the result, or um, if you want to know directly the paper, you can arrange some schedule with me. So you can arrange schedule with me what time you want to go to my office, and we can arrange the schedule, and you can find out the paper and maybe check out your score by yourselves, okay, by looking at the paper. Or if you want to know directly, you can email me. Some of the students already email me to know their score. So you can also do that for the midterm result. Okay. I think the average is not too bad. I think 69, the average for the midterm. So I think it's good. Okay, I think we can start chapter 15. So don't forget to watch. Don't forget to watch the additional video that I prepared. So I prepared the 14.8 and chapter 14 exercise. This week I will prepare another video for chapter 14, so you can also watch that. Okay, maybe this Wednesday or this weekend I will upload. Okay. Okay, we can move to start our course. So we can start a new chapter, chapter 15. Okay. The overall topics for chapter 15 is multiple integrals. So we may have at least two integrals, double integrals, or triple integrals. Okay. Now to start, we will start from double integrals. Okay. Now let me start from just a little bit review on calculus 1. That is, we have this integral, right? So what does it mean? It means that this is area under the curve of f of x, right? From x equal a to x equal b, right? This is what it means if you want to visualize the integral, right? Now in the calculus 2, what we are going to evaluate is not area, but it's volume. So let me write this as volume. Okay. And let me give you this is what we did in calculus 1, right? Or maybe I'll put here, about here, and maybe this around here. But let me go through some visuals for what it means by volume. So remember that you have a surface z. It's a function of two variables for the z here. So you have you have a surface like that, and you take out some of the regions from those z, and we can evaluate as this volume. Okay. Now, of course, we have this r. The r means rectangle, so we have rectangle x, y, right? Oh, wait. Okay, let me write some of the introductions on this integral. Okay, so given a functions of two variables. In our case, this is z equal f of xy. Okay, that is continuous and non-negative on region R in xy plane. The volume of the solid enclosed between the surface Z and XY plane is equal to volume of parallel pipe. Okay. And region R means that this is from AB multiplied by CD. A less equal X less equal B. And then C less equal Y less equal D. Okay, what we can do from this notions for the volume, if you want to calculate the volume of parallel pipe, now it's better if we are going to cut the region here. And we can make small square or small rectangle. Okay. And then we projected also this cut to the surface. So we are having rectangular shape like this. Okay. Okay. Now let me go through. Okay, we can make this kind of cutting. So we are going to have small region here. Okay, small region, and we can choose our sample. So instead of just xi, as usual we have in the original integral, we have also j, because we are having the rectangle x and y, right? So this means that it's correlated to that axis I, j. Okay? And we have this sample point here, and we are going to evaluate this as the volume of parallel pipe. So the volume will be equal to the height, which is the f, and then multiply with the base. The base is the area. So this is height and base. So practically this is how we can approach at the very beginning. Okay. And now, because we have a lot of rectangles, we can do some summation to add all this rectangular shape, the box. Okay. So we can take this into or approach or approximate the sum. So this is from I equal 1 to some m, and j equal 1 to some n, and then f, the height, okay, I hope you don't get confused on this. This is practically similar with calculus 1, but we have two summations. So summation 1 is for I, which means the x to some n, some m, and the second summation is from j, which is the y to some n. Okay, and this is the functions. It's a function of two variables. So this is actually z, but we can write as a function of x and y. Okay, and then multiply with the the area. Okay, and then from the summations, we know that this is our approximation. And based on the definition of the summations, if m n going to be large enough, if we slice the box really small, means that m and n, the numbers will be really huge numbers. Then we can take the volume as the limit, as m and n, both going to be infinite numbers of the summation. We can take the limit, and based on our understanding on this limit definitions, this will be equal to integrations, because two summations, and we can write, or maybe let me write on the sides, let me write here, double integrals for some r. This is f, xy, and dA. So this we call the double integral over rectangle R. And how to operate, let me just explain later on after this page. Okay, so you can write at least the definitions for the notes, the definition for double integral. And this limit should be provided that the limit exists. And we can say that the function is integrable. Okay, let me go to more practical use of this double integral. Okay. Let me go to the next page. I hope you finish this part, or at least you can take screenshot if you want. Okay, let me go to the next page. Okay, notes. Here's some notes. If the functions have both positive and negative, then the volume is the difference in volumes between the region R, and surface below and above xy plane. Okay, let me give you the formal definitions, that if the function is positive, then volume of the solid that lies above rectangle R and below surface C. We can write this fxy dA. And the practical take for this volume, for example, if I write this f of x, y, and then this is dx, dy, we can write dx, dy, or dy, dx, depends on the case. If this is a, b, c, d. Okay, how to integrate this double integrals? Okay, so first, what we can do is first we can integrate the inside, this dx. Okay, this is the first step. And then the second step is integral to the outside. So first step, the inside, you integrate. After you get the result, you integrate once more to the second step. Okay. Okay. Example. Okay. For example, we call this iterated integrals. For example, let me write x squared y, but then dy dx. And then this is 1, 2, 0, 3. So the first thing we can do is we take the inside and we integrate. So first we take the x squared as a constant and y will be our variable. So this is the result. We take the numbers from 1 to 2 and still write 0, 3 and the x. Okay, we solve this first. Remember this 2 and 1 is for y. Okay, so we can do for y first. So we will have 4 over 2, so 4 over 2x squared minus 1 over 2x squared. Or we can say we have 3 over 2x squared. And from here, we still write 0, 3 dx. And then this equal, we integrate to the x squared. So we will have x with power 3 divided by 3 multiplied by 3 over 2. So we have x cubed over 2 from 0 to 3. So we will have 27 over 2 as the result. Okay. So first, that is how we can use the double integrals in practice. What about if we exchange the dy and dx? If we exchange the integral endpoints, okay? So in this case, because it's a constant, we can exchange that this is 1, 2, 0, 3. This is x squared y, and then dx dy. So let's evaluate this part. Okay, let's evaluate this part. So outside integral still 1 and 2. The inside we will have with dx. So x squared become x cubed over 2 and y. And then we take from 0 to 3. And this will be dy. Okay. Still we have 1 and 2. So we put 3, this is 27 over 2. Oh, it should be 3, sorry. Should be 3, okay. So 27 over 3y. And then this will be dy. So let's evaluate this. 27 over 3, y become y squared over 2 from 1 to 2. So this will be equal to 27 over 6 y squared. So 27 over 6 y squared is 4 minus 1. So it should be 3. So should be 27 over 2. So we get the same result. So actually, these iterated integrals can be substituted or exchanged, dx dy or dy dx. No big deal, still the same result. Okay. I will write the theorem probably down here. We call this the Fubini theorems. So it say that if the functions continues on the rectangle R, let's say R is equal xy and then A, x, b, and c. Let me put a little bit left. C less equal y less equal d. Okay. Then we have double integral over region R fxy dA. We can write this. Let me put a little bit left. fxy dy dx. This is a, b, c, d, and equal fxy dx dy, and then we can exchange this a, b, c, d. So we can exchange this region and exchange which one you are going to evaluate first, dy or dx. Okay, maybe any questions so far? Okay, so remember this double integral in this 15.1. This is happen on the rectangle, okay, over the rectangle. Okay, the rectangle means that the area that you are observe, which means this area here, the area you are observe here is a constant. It's a fixed constant. We can imagine that although it's small numbers, it's a fixed constant. Okay, so what we have here, the A, B, C, D is all constant. Okay, because in the next sections, we will see that the endpoints could be a function as well, and that will be a little bit complicated, and you need to be careful when you are using this theorem to exchange dx and dy. Okay. Sometimes it's easily changed, but sometimes you need to make sure that it's relevant and it's okay to exchange. Okay. Okay, let me write some property on this double integrals. Some of the properties are familiar and you know well for those integrals. But let me write some of the property for you. Okay. If you need to write notes from the previous page, let me know. I will turn back and you can take some screenshot if you want. Okay. So some properties. You have C as a constant. C as a constant. Okay, and as usual, we can factorize C. And if you have addition inside the double integrals, you can separate these integrals. Okay, and if you have subtraction, also the same. And if you want to make some separations on the rectangle, you can also do that. So we can make the R1 and R2. Okay, and last one, I think the most important within this multiple integrals is if you have two functions, let's say g of x, and h of y. We can write this as separate the gx with dx and separate the y with dy. We can also do this property. And to prove the last one here is, I think it's easily to be proven using the Fubini Theorem. If you want to make it more clear. So if we have this is C, D, A, B, we have two functions, function of x and function of y. Let's say we start from the x dy. So first what we can do is we write the outside integral and we write the inside as a b gx h y dx and write the dy also. So when we integrate the this inside integral with respect to dx, we can write the function h as a constant, right? It's similar with partial derivative. When we integrate, we can also put the other variable as a constant. So we can take this, h goes to here, and still we can integrate the inside. And by doing so, we see that we can grouping this h, y into one group and the g of x things as one group. Okay, this is through the Fubini theorem. The Fubini theorem. Okay, uh, one more sections on the 15.1 is the average value. Average value of functions. So recall in calculus 1, you have the average value as 1 over b minus a, and the integral of a to b f of x dx. Okay. Now the average value in calculus 2 will be, so it should be having similar structure. That is, this will be not b minus a, but it's the area. So area of R, and then this will be double integral, and this will be function of x, y, dA. Where A is AR is area of R. So it means that we can write that the area multiplied with the average, this will be equal to the double integral itself. So actually, by using these notions here, we can take some approach um, to describe the average value of some volume. Like for example, you are going to evaluate the volume on maybe on sands or snow. Okay, like you have a specific volume of that, and you want to know the average value. If you want to take some samples and take it into double integrals for the whole area, you can do and take the average value, and then by those average value, if you multiply with the some area of the rectangles, it will be going to evaluate the whole area by using the double integrals. It will be equal or approximately equal. Yeah, approximately equal. So I think that's all for the double integrals in over the rectangle. So perhaps I will give you some of the questions before we move on to the 15.2. Okay, let me check the questions. Okay, let me give you some example, maybe 2 or 3 example to help you at least familiar with the double integral, and we can have a warm up. Okay, some exercise. So let me give you questions. Okay, you can try these 2 examples first. Okay. Okay, we can start from the first one. So we have ln y over x y, and then dy over dx. Okay, first what we can do, we can group the x and y. Okay, so first we can separate this x. Okay, we can separate this x and write 1 over x, and the x is this 1 over 1 and 3, right? And we can write this first, and then the second one we can write with different color. Let me write in green. You can write 1 5 and y over y dy. Okay, now 1 over x, this will be ln x from 1 to 3. Now what will happen with this ln y and over y? Okay, to solve this, you need to remember some of the techniques in calculus 1. So that's a little bit, you need to have more review on calculus 1. So to get this solved, we can substitute with u substitutions and substitute with ln y, because when we have du, this will be 1 over y dy, right? We can substitute dy, y du. Okay, so if we write in different space here, we can write that ln y is u. Let me write integral, and over y, and then dy become y du. So we can cancel this, and this is u du. We can write as half u squared plus c, right? but this is just to note that we have this u squared, and we can write u squared as ln y squared. So we can write that in our equations here. So you can write ln ln y squared over 2 from 1 to 5. Okay. Now we can input the numbers. So ln 3 minus ln 1, so that's it. And then multiply with ln y, ln 5 squared. So ln 5 squared. And then ln 1 is 0, so we just have this. So we have half ln 3 ln 5 r squared. Sorry. Okay, we can just leave as it is, or if you want to make the simplification, I think you just write this. I think this should be okay. Okay, so don't forget to review some of the techniques, at least substitutions, and I think the integral by parts. Okay, most case we are going to use that a lot. Okay, now the second question. I would like to what to do first here is we have x minus y in the power, right? So what I would like to suggest is we can separate this power, okay? So first we can just write as it is double integrals and write the y, e x, and e minus y, okay? And then the x dy. And as usual, we can separate this into each of variable x and y. So we can separate with x and then with y. Okay. Now e to the x is just e to the x. E to the x from 0 to 2 and multiply with, we can have integration by parts, right? Integration by parts, integration by parts. We can write y, e negative y. This is derivative, this is integral. Let me write for you. This is 1, 0. Integrate this will be this, and integrate one more will be this. So we will have plus minus, so negative e minus e. Oh, sorry, should be y. So we will have negative 1, negative y, negative 1, negative 1, and then multiply with e, negative y. Okay, I think that's our integration. So we can write here negative y, negative 1, e, negative y, and then we evaluate from 0 to 1. So this will be e with power of 2. Don't forget e with power of 0 is 1, so minus 1. And this parts will be negative 2, negative 2, e, negative 1, and minus 0, it's negative 1, e, negative 0. So this should be equal to e squared minus 1. This will be plus 1, so 1 minus 2 e with negative 1. We can simplify it if you want. If you just stop here, I think it's okay. It's okay here if you want to stop. But if you would like to calculate the row, oh, this should be minus 2. Okay. If you want to write here, also okay. Unless there are some options in the questions, like you need to choose which one, and then you need to make sure that the form is correct. Okay, the form is correct. Okay, any questions from this part? From these two example? Any questions? Okay. Yeah, I think Oliver, the example already here, right? You want to have an example on the last property? Okay, I think it's okay, right? I give you the example from these two example, right? Okay, so if no questions, do you guys already scan the QR code for all of you, or no? Who hasn't? Okay, let me give you QR code. Okay, so if you haven't, you can scan the QR code for one. Okay, we can continue. Do you feel it's too fast or it's okay for the integral, the double integral? Do you feel the lecture is too fast or still okay? Okay. If you feel too fast, or maybe you need to maybe write some notes from the previous page, let me know. Okay, you can write on the chat box, like maybe you can write, oh wait, I want to take notes, or I want to take the screenshot. You can just write on the chat box. So every time we are going to move to the next page, I will just let you know that okay, I will move to the next page. So that means that I will turn out supposed to be negative 2e. Oh, yes. Correct. Okay, correct. Okay. Yeah. Should be negative 2e because it's supposed to be cancelled, right? Yeah. Correct. Good, Eric. Good. Good observation. How about the other one? Is there anything that maybe some mistake here? I think it's okay, right? Maybe I will attach further exercise for 15.1. But basically 15.1, you deal with the notions of double integrals, and the integrals is having a constant. Okay, so for example, this it's like a definite integral. So you have a constant here, constant, and nothing, not really a big deal for calculation. You can separate x, y, and you can do, for example, if you want to make the 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 inside integral first and then outside integrals, that's also okay. Nothing, no big deal. And if you have like something a little bit complicated like this, you can separate, become x and y, and you can integral each one of them and then multiply at the end, and that's also okay. And also the double integral in the 15.1, you can actually given questions like you have a surface and you need to calculate the volume within specific rectangles, and you can just put into the double integral with a constant, similar approach, similar calculation and method. So it's not too big deal. Okay, if you have time, we will have more explorations on this double integral. But the more I think I can say difficult is if we have um, the the endpoint is not a constant. So if we have another function, that will be a little bit complicated. We need to deal with that also. Okay, I will move to a new page and given out the other sections, which is 15.2. This will discuss the double integrals over general regions. So we are not focused only in just a rectangle, but we can have some much more general approach to more shapes. Okay. Okay. Let me give you, or maybe let me give you just illustrations, rough illustrations. So if this is having a surface, maybe surface you have this, right? And you can project this surface to the plane, and you will have maybe here, and we say that we have D at the bottom. Okay. This is functions of xy. Okay, so if we observe this D, okay, we want to observe this D. If you just checking at the y and x axis, we have D like that, probably like this one. So consider this as general region. So consider D is general region. But we can suppose we can make this general region inside some restrictions. Okay, we can make it into a box like this. So suppose this is another r, okay, the rectangle r. So we can make our function into a piecewise definitions. That is, this is equal fxy if xy in domain of D, and it will be equal to 0 if the points is outside of D. So it's in the R, but not in D. Okay, of course, that is what it means is if the points here, it means that it will be 0 because it's not projected to the surface, right? So we can say it's 0. So we can have this definition to help. Okay, so this definitions or this description is to help us to observe the at least the area of the projection of the surface. Okay. So if this f integrable over r over the r, the rectangle, the blue one, okay, then we can write down the double integrals over d of f xy dA is equal integral of r f x y dA. And basically what this capital F and small f means that, so the capital F is just our we say the functions, the whole functions that includes D and R. Okay. But the small f, we are focused only on the surface that we are going to evaluate over the region D. But of course, it will be logically make sense. Okay, if we want to calculate just this small f in D, then we can look on more general functions. That is, we say the capital F. But when the point is outside D or still in the rectangle R, we can say this will be 0. So we can say that this is pretty much equal. What this practically means, okay, let me make this a little bit smaller and put here resize a little bit, and this also resize. Okay, now let me put. Okay, what does it mean is if we project, okay, okay, if you project this f, this is just what we have here. But of course, we will have some difficulty to make sure that what will be, okay, what will be the shape or the area of D, because it's D can be any shapes, right? So to help us to define this D, we can take another approach that is the graph of f, and we are just focusing on D. And we can say that we have this as the area of the R to help us to calculate actually. And the area of R outside D, this will be turns out to be 0, right? Because there is nothing at the above them. Now from here, we have at least two types of D. Okay, from here we have two types of D. Let me write here. As an implication of our discussion here, we have two types of D. Okay, if you still feel confused over what we have definition here, just focus on these two types of D, and then you will see what it really means. Okay, what it really means. Okay, so I will move to the next page. So hope you finish this part. Okay, let me give you the official definition on what these types mean and what's the implication and what we can do to make it more easy to understand. Okay, so first let me go for a little bit official, a little bit some words definitions. So first there is type 1 definitions. So type 1, D lies in graphs of two continuous function of x. So we can say that D, the point in xy, that having x, and for y is having a function. Not g prime, it's supposed to be g1 and g2. Okay. So what it means is, I take this approach here. So it's what it really means. So the D can be described first described in a function of x. So we have function of x. And another function of x here. So you can take separation here. And another function of x. This and 1 and 2. Okay. So we can write down for type 1, we can have D so A, B, G1, G2, okay, so we have, remember, because we are going to evaluate this function of x to make it more make sense to our calculations, this is supposed to be dy because y is function of x, right? That's our in the definition here, the domain. Okay, so we can put the x as outside integral like that. Okay. So let me move to type 2. Type 2 is giving you more clear that is function of y. Okay, so we have only two types, function of x and function of y, which means that the D depends on your observation. Sometimes some D we can make it into function of y, we can make it into function of x. Depends. It depends. Like this case here, I think this case we can make it into some function of y, right? It's possible. It depends on what we can observe. Okay. Now if we have here that the d will be in between of c, y is between c and d, and we have h1 and h2 for for x. Should be h1y and then h2y, where h1 and h2 is continuous. So this is function of x. This is d lies in functions in between functions of y. And the integral we can write and now we can write dx dy. Okay. And for me to suggest you, so this is type 2, to suggest what can we do on this type 1 and type 2 is it doesn't matter. It doesn't matter. And I don't really suggest you to memorize this part. What you can do is, first, if you can make out that the area, the D, maybe we have this. Of course, this will be results in a function of x, right? So this will be goes to, we will have, this is functions of x, function of x, and then we have our functions, let's say g, x, y. And of course, this will be supposed to be dy, dx, and this will be should be the x, okay, the x that you are going to evaluate. For example, maybe evaluate from a to b. So a, b, like that. Or if you have the area D, will be having an obvious choice for a function of y. So you can take this as maybe function of y, and let's say this is g, x, y, and this is the x, dy. Maybe c is here, and d is here. Okay, this is just to show you what we can do on more practical. So you don't really need to focus on okay, this is type 1, type 2. Nevertheless, no need to really make difference in type 1 and type 2, because sometimes you can also make some exchange in x and y. Depends on the function, right? Sometimes you can make function of x become function of y, and sometimes it also reverse from y to x, from x to y. It's okay. It's also it's up to you which functions you are going to evaluate. Okay, let me give you a more I think more example on how um, we can take uh, the example. Okay. Okay, I will move to the next page. Okay, let me give you an example. Okay, evaluate this integral where d is bounded by y equal to x squared and y equal 1 plus x squared. Okay, now to understand on how we can solve this, if you want to draw, or if drawing the functions can help you to see the solutions, then we can draw the double integral. But if you want to directly calculate and you know how, and that's still okay. But let's say we are going to check the d. So we can draw our d. So we're drawing our x and y axis, and we are trying to draw our 2x squared and 1 plus x squared. First, maybe let me draw 1 plus x squared, because it's just our x squared and shifted upwards 1 unit. So it will be, the vertices will be around there. So let me draw. Okay. Maybe this is the drawing. So probably this will be y equal 1 plus x squared. Okay, now the 2x squared is maybe around here, going there. Although it's not proportionally similar, but let me just write this, y equal to x squared. Okay, maybe to make sure the points, because we want to evaluate the area here, right? We are going to evaluate here to make our d, right? So we can take the equations to have our point of intersection. So x is plus minus 1. So when x is 1, y is 2. When x is negative 1, also y is 2. So this will be 1, this will be negative 1, and this will be, yeah, this should be having more proportional, but this is 2. Okay, now from this we can take this, and since I think we can just leave as a function of x for this 1 plus x squared and 2x squared, so we can say that this is going from 2x squared to 1 plus x squared. Okay, still you need to remember the top and bottom of the integrals, right? And negative 1 to 1, and the functions inside is x plus 2y. This is the surface, okay? And then dy dx. Okay, now to avoid some mistake, because this is, I think, some mistake that may happen when you mix up calculus 1 and calculus 2. Okay, so first is, this is the function that we are going to evaluate. This is function of xy, not this two. Okay, these two are the functions for the d, or the this, or the domain that we are going to evaluate for the integration. Okay, but the deal is we are going to evaluate this, or we can say the surface, right? Because sometimes you can have like a mix up with calculus 1 and calculus 2, and you're ended with just evaluating the area, not the question itself. Okay, so we can evaluate this, and first we can evaluate the inside integrals. So evaluate with respect to y, we have xy plus y squared, and then we can write the evaluations and then the x. And then we can have x 1 plus x squared plus 1 plus x squared. This is a little bit complicated, a little bit having some calculation here. And then minus x 2x squared 2x squared, yeah, and then minus, because it's plus, so minus y squared 2x squared squared. Okay, and then the whole, still we have the x. So calculate first all the things inside. So x plus x cubed, let me write here, maybe to help, let me write all the things here. 1 plus 2x squared plus x4, so 2x cubed, so it's plus plus, this is minus, and minus 4x with power of 4. Okay, so power of 4, we can write negative 3x with power of 4, and then plus x cubed minus x cubed, and plus 2x squared plus x plus 1, and then the x. And then evaluate, we still have some integral here. This will be negative 3 over 5 x5, negative x4 over 4 plus 2 x cubed over 3 plus x squared over 2 plus x, and then evaluate from negative 1 to 1. And I think you can evaluate this, okay? And you can use calculator if you want. Okay, so I allow calculators for most of the part for integrations. It should be 32 over 15. Yeah, allowed for calculator, for calculations, okay? But of course, if the question is giving you some choices, then you need to choose wisely. Choose wisely. So the difficult part is actually not the calculations. The difficult part is to know which one is you are going to integrate. I think I'm giving you this example to show you that we can have this functions as our endpoints for the integral. Right? And imagine if we have triple integrals. Later we will have triple integrals. So it could be having some trouble, right? So the difficult part is not to calculate the numbers. The difficult part is to imagine how the visuals looks like. Which one is your endpoint? Yes, that's the key, Oliver. That's the difficult part actually. To know which functions and what kind of functions, or maybe you can exchange the function of x, function of y. That depends on you. When we set up wrong integrals, even you are using calculator, you end up with wrong calculation, wrong result. If you take wrong path for to ensure which one is the functions, you will end up with wrong result. So the difficult part is actually to draw and to visualize. Okay. Let me give you more one more example on this part. Okay, another example. Evaluate double integral xy dA, where the bounded by y equal x minus 1 and y squared equal to x plus 1 plus 6, sorry. So first, to imagine how it looks like, we can set up the functions for the region D. You can write the y squared as y if you want to take this, or we have this, right? We have two y if you want to make it into function of x. But of course, if you see y squared, my suggestion is to take the function of y. So we can take x, right? We can take x, or 2x, y squared minus 6, and x is y squared minus 6 over 2. And then this y equal x minus 1, we can take this as y plus 1. And we can take the point of intersections. So we can write the intersection of line and parabola as y plus 1 is y squared minus 6 divided by 2. Let me write this is plus 2. And we still write minus 8. So we will have y minus 4 and y plus 2. So y is 4 and y is negative 2. So we'll take this a little bit longer here and write this is -2, this is 4. Okay, so this should be around here. And this is 1, 1. This is the x, y plus 1. Should be having, we can check our vertices from here. So minus 2, so 2 over 1 over 2. So it should be 4, 6, should be -3. So at 0, it should be -3. So -3 is, this is, sorry. So 0, 1, 2. I suppose this is the vertex. Okay. Probably that is our D. So D will be about that. So you can write dxy dA is equal -2, 4, and then the functions will be, this is the half y squared x equal -3, right? So from this half y squared -3 to y plus 1. And then xy dx dy. Okay. Okay, first, to set up this double integral is important. So if it's like step-by-step solutions, then this step is worth on at least 25% or 30%. Yeah, 30%. These steps. And then you can set up the integrals. So we can do the inside integral with respect to x. So we'll have x squared over 2 and y. So we can set up evaluations from half y squared minus 3 and y plus 1. And then dy at the end. So we can substitute y and then substitute the or maybe factorize half outside to make it easier. So x squared, so y plus 1 squared minus half y squared minus 3 squared, okay, and then dy. Y squared plus 2y plus 1 minus y for y4 so this should be y plus 4, right, plus 1 minus 8. Oh, sorry, plus 2y first, plus 2y minus 8. Okay, and then multiply with y. Let me write first. This will be negative y 5 4 plus 4 y cubed plus 2y squared negative 8y, and then integrate with dy. And then this will be negative y624 plus y4 plus 2 over 3y cubed minus 8y squared of 4. From negative 2 to 4. Again, at the last step here, think you can do with calculators to get directly the answer. Okay, then if we look back on if we are using this function of x, actually we still can solve. Okay, we still can solve. So if we take the y, for example, if we have plus 2x plus 6 and then minus 2x plus 6 for this y, then we would have, at least for the first functions, for function of x, let's imagine if we have this negative, then this will be from negative 3 to x to negative 1. Okay, so if you see here from these two parts here, so this will be having two components for this part. This is negative 1, negative 2. This is 4. Oh, sorry, 5, 4. 5, 4. And this will be 0, negative 3, 0. It's not 1, it's negative 1. So from negative 3 to negative 1 means that from negative 3 to negative 1 here. From this to this, we have negative, and we will have x minus 1 from negative 1, x 5. So negative 1. So negative 1 from here, negative 1 to 5 to here. It's a little bit complicated, of course. So if we would like to evaluate, so this xy dA is from negative 3 to negative 1, and from negative to x plus 6 to 2x plus 6. xy dy dx plus double integral from negative 1 to 5 from x minus 1 to x plus 6 of xy dy dx. But of course, this is much more complicated, right? Complicated works that you can do. So better to just exchange into. Can they calculate the double integral? Not sure. I think depends on the calculator. But I think if you just take the normal one, I think just a single integral, I think. So necessary way or works that you can imagine in this part is first draw region. That's necessary, I think. Second, reverse order if necessary. Okay, if necessary, using the Fubini theorem. So you can try dy dx dx dy, means that if you can take function of x, if that's easier, then do the function of x. If you need to exchange to function of y, and if that is way more easy, change to function of y. If not, then you can imagine this integrals here. This integrals is quite difficult, right? So it doesn't matter like the type 1, type 2 you have before. Like it's not for memorization. It's just to visualize if you have function of x and if you have function of y, what could be for your region. Right? That means you can do both. You can do both for some functions, and it depends on your preference, which one is the best way to solve. Okay, another important things on uh, this part is the how to change the order of integrations. Okay, what should be our concern? Okay? That's raising a few questions. Okay, I will move to the next page. I hope you finish this part, and if not, then you can take screenshot for a while. Okay, I will move to the next part. Okay. Okay, let's have um, evaluate this. Okay, how to solve this? So if we stick to the rules that we are going to evaluate the inside integrations, then we need to integrate this part first, right? Sine y squared dy. What can we do? Can we integrate this? The sine y squared is not elementary function. Which means that we are not going to have some finite terms. Okay, so no finite terms. So suppose we are going to evaluate this. What can we do? So perhaps if we change this order, becomes dx dy. So we can change this order. Then perhaps we can solve this. If this is dx dy, sine y squared dx, we can integrate, right? We can just multiply with x. That's the integral, right? For dx. But how we can change this integrations, the double integral for the endpoints, how to change? So first, if we have, let me write as a more general d sine y squared dA. Okay, so d, we know that for each point xy, the x will be from 0 to 1, right? If we have looking at these integrations, and y will be from x to 1, okay? Okay, now to get more understanding, we can sketch these regions. Sketch the region. So from 0 to maybe 1 is here, and then y is having equal x. Okay, so we have y equal x, and then until y equal 1, maybe here. So y equal 1, maybe here. Okay. And if you check with our conditions, we have x from 0 to 1, we have y from x to 1. So this is our region, right? Our region. Okay. Careful, because sometimes if you not really pay attention, you may end up with the other part as your region, and that's wrong. So okay, if you have this, then we can take the order of the integrations. We can write d sine y squared dA. We can write, if we want to make dx and dy, so perhaps we can take y from 0 to 1, right? From 0 to 1. And x. X is from 0 to y, right? So if y is from 0 to y, so this is y, and x is from here, from let me say from here, so x will be a variable, so we have x here. Okay, so we will have from 0 to y. Okay, so we will have 0 to y. Okay, now we evaluate, this will be sine y squared and then multiply with x, and this is from 0 to y, and then dy, dy. So we will have, this is y sine y squared dy. And we can do the substitutions. So u is y squared, so du is 2y dy, so dy is 1 over 2y du, so we can have half integrations 0 1. So we will have sine u become negative cos, so we have negative cos y squared from 0 to 1. So this is wrong here. So we will have half negative y squared cos 1, so 1 minus it's positive, so 1 minus cos 1. Okay, so that's how we are going to have a change in order for the integrations. It's a little bit you need to have good visualizations, good imaginations, and to help you change these integrations is to draw the area first, to draw the area of the rectangle or the area of the domain, okay? The D. So this is important. So draw this region, draw the region. It's important. Okay. And careful. When you are dealing with the integral is over functions, then when you are dealing with this and you make some mistake and make that y gone and become a constant, maybe 1, okay, it means that if you have the rectangle, right? So it will be a different solutions. So careful on that. Okay, I will stop until here. If you have any questions, you can write in the chat box. Okay, if you have any questions. Okay, any questions? If not, then this is the end of our lecture today. So remember, we will have online quiz for chapter 12 and 13. I think I will put the notes, what we have in chapter 12 and 13 in the Moodle today, and also giving you some attachment for exercise for chapter 15. So please check it out. Okay, so if there's no questions, so you can leave these meetings and see you on Friday. Okay. If you have any question, you can ask me. Yeah, you're welcome.